Hello students. Today we are going to study one important system block of Lpc2148, that is PLL, phase lock loop. Okay. So phase lock loop in Lpc2148, it is basically used as frequency multiplier. So it will increase the clock frequency in the Lpc2148. There are two PLLs are present in Lpc2148. One is PLL0 and second is PLL1. PLL0 is used to generate the CCLK clock, that is system clock. So you will always come across this term CCLK clock in the further discussion. PLL1, it is actually supplying the clock for the USB and it is having a fixed frequency of 48 megahertz. The USB clock is 48 megahertz for Lpc2148. Okay, so we are going to study phase lock loop present in Lpc2148. There are two PLLs present there in the 2148. One is to generate the system clock and the second one is to generate the clock for the USB. Okay. So here this is roughly the block diagram for the PLL0 and PLL1. So system functions where you are going to actually generate the clock signal through the crystal. So oscillator is present there. So crystal is connected to the oscillator by using the two pins XTAL1 and XTAL2 and reset pin is also used there. So the output of the oscillator is given to the two PLLs, both PLL0 and PLL1. So the output of PLL0 is working as a system clock which is used to drive only the processor part or CPU part of the PLL, and PLL1 output is used as USB clock. Okay. Now we will concentrate only on PLL0. So for PLL0 we will see some fundamentals of the clock signal of ARM microcontroller. Okay. Use external clock signal can either use external clock with duty cycle of 50-50, that is 50%. So its range is 1 megahertz to 50 megahertz. Okay, so you can directly connect one or external clock signal to the controller whose minimum frequency can be 1 megahertz, maximum frequency can be 50 megahertz, and it is connected to the crystal 1 pin. Through that you can give the external clock signal. Second one, by connecting the external crystal oscillator, that is crystals are connected there, an internal oscillator is used. So here the frequency is 1 megahertz to 30 megahertz, but you are not using the PLL here. Here also you are not using the PLL. And the third one is you can use on-chip PLL oscillator. Here, the external clock frequency ranges from 10 MHz to 25 MHz. Mean you can connect the crystal of 10 MHz to 25 MHz, or you can take it from the external clock signal, but that will be limited to maximum 25 MHz. Okay, and now it is given to the internal PLL. So how actually the system clock and peripheral clock works, that is given here. So crystal oscillator or external clock source is given as input to the PLL0 and its frequency is denoted as F oscillator. Then the output of the PLL0 you can call it as a processor clock or CCLK. Okay, and the processor clock is given as input to the APB divider whose output is considered as PCLK, which will be given to the peripherals. Okay, so APB divider is going to generate PCLK. In programming, sometimes it is referred as VPB divider. Okay, so both are same. So we will concentrate on PLL0. It generates a clock signal with reference to an input signal generally from a crystal oscillator. And it is used to increase the frequency of clock signal of microcontroller. Okay, so you can get exactly the working of the PLL0 from this diagram. So this is the oscillator present inside the 2148 and one crystal is connected to the oscillator, and its frequency can be 10 megahertz to 25 megahertz. Any frequency you can generate there using the crystal. Okay. Then its output is given as input to the PLL0, where it is internally using current controlled oscillator. Like VCO. VCO was voltage controlled oscillator, which we have seen in the definition of PLL. Here you are having current controlled oscillator whose frequency range is given as 156 megahertz to 320 megahertz, and its output, it is driving it. Again the output will be a one decreased frequency, and that frequency is given as CCLK or processor clock, and that is 10 megahertz to 60 megahertz. Okay, so now we will see the registers of the PLL. PLL con, that is PLL control register. Configure CFG, PLL configure register. PLL stat, that is status register, and PLL feed, that is a feed register for the PLL. So four are there: control, configuration, status, and feed registers are there. Okay. So the first one, PLL control register. So PLL control register, uh, basically we are interested in two things. One is PLL enable, PLL E, and second is PLL connect, that is PLL C. Okay, these are reserved. This is wrong. PLL enable, it is when one and after a valid PLL feed, this bit will activate the PLN and allow it to lock to the requested frequency. So it will turn on the PLL. And the second one is PLL connect. So when the PLL is working, it will not immediately give you the required frequency. Say for example, if you have designed PLL for the external output frequency of 60 megahertz, it will not immediately generate 60 megahertz. Okay, but it will generate some, it will vary it. Okay, so that time is called as locking period, or it is a time period after which the PLL is locked to that frequency. Okay, and therefore you need two different things. One is enable, means you are turning on the PLL, and the second one is connect, when you are going to connect the PLL output to the system as the system clock. Okay, so two different things are there. So this is the first one. This is the first part you are doing there, and this is the second part you are doing. You will first always enable the PLL, and after that you will connect the PLL. So for that you are going to use PLL control register. So remember, only two bits are important. This is 8-bit register. Don't forget. In case of LPC2148, for the UART, some registers are 8-bit, okay, or 16-bit also. This is exception present in case of 2148. So this is the PLL control register we have seen. The next one is PLL configure register. PLL configuration register, again bits 0 to 4, that is 5 bits. These are 5 bits. Then 5 and 6, these are 2 bits. These are important. Okay. 0 to 4 bits will decide the M cell, that is PLL multiplier, and 5 and 6 bit will decide P cell, that is PLL divider. P, that is divider, is used. Now these two are required in case of the frequency calculations. So at the time of the frequency calculation, I will show you both P and M values for the PLL. Next, PLL status register. Whatever we have seen earlier, all those bits are part of the status register. For example, M cell, multiplier selection, P cell, divider selection, PLLE, that is PLL enable, PLLC, that is PLL connect, and one more is there, PLL lock status. So all these things, if you want to read what is the current status of the PLL, if you want to read, you can use status register. So what it will do? It will read the value of PLL multiplier. it will read the value of the PLL divider, it will read the value of the PLL enable bit, it will read the value of PLL connect bit, it will read the value of the PLL lock status, or it will reflect the PLL lock status. Okay, so these 5 things are given by the status register. So remember, 0 to 4 bits are M cell bits, 5 to 6 bits are P cell bits, bit number 8 is PLE, bit number 9 is PLLC, and bit number 10 is P-lock. So this P-lock is used in between enable and connect. So first you will perform PLL enable, second you will check PLL lock. Unless and until PLL is not locked to the requested frequency, you cannot go for the connection. And then third one is you will activate the PLL connect signal. Then PLL feed. This is another different thing. You can call it like a key and lock. So it is like some security provided for the PLL. You cannot easily alter the values for the PLL. If you want to change the values for the PLL, you have to use PLL feed register. A correct sequence must be returned to the PLL feed register in order for changes to the PLL control register and PLL configure register. The feed sequence is AA and 55. This sequence must be given in the same order. First A should be given there, and second 55 should be given to the PLL feed register. Then only it is going to reflect your changes in PLL control register and PLL configure register. Okay. The two writes must be in correct sequence and must be consecutive APB bus cycles. The latter requirement implies that interrupts must be disabled for the duration of the PLL feed operation. Okay, so just forget that. Just remember that for PLL feed, first you have to give AA and then 55. This is very important. Okay, this sequence is very important in case of the PLL feed registers. Without that, circuit will not work properly, or the changes will not be reflected. Next, some required things we will discuss there. One is F oscillator. This is the frequency of the crystal oscillator. This is the first term we are going to use. Second is FCCO, frequency of current controlled oscillator, frequency of CCO. Third is CCLK. CCLK is nothing but CPU clock frequency or PLL output frequency. The next one is M, that is PLL multiplier value. It is set using M cell bits in PLL configure register. P, PLL divider value. It is set using the P cell bit in PLL configure register. Then PCLK, peripheral clock from CCLK. Okay. So remember F oscillator, FCCO, CCLK, M that is multiplier, P that is divider, PCLK is a peripheral clock. Next, some important equations regarding the PLC frequency calculation. It is better you take down these things because definitely it will be required for your programming purpose. CCLK is equal to M into F oscillator. That is processor clock is equal to multiplier into crystal oscillator. Or CCLK is given by another formula, that is FCCO divided by 2P. So current control oscillator frequency divided by 2 into divider. That will also derive the CCLK. Means if F oscillator is given and if CCLK is given, you can design the multiplier for M and P values. Okay, you can appropriately design. So F oscillator and CCLK will be given there, and according to that you have to design the PLL. Then the another one is FCCO is equal to CCLK into 2P, or FCCO is equal to F oscillator into M into 2P. So the upper two equations are modified here or rearranged to get the lower one, that's frequency of CCO. Then we will go to the program. How to write the actual program for the PL. So for that, we are writing the code for setting up PL. There are 4 steps are there. One is set up the PL, then apply the field sequence, then wait for the PLL to lock, and fourth one is apply the field sequence. Okay, wait for the PLL to lock and then connect PLL, and fourth one is apply the field sequence. Okay, again the frequency calculation we have already seen this, the same thing is given again. So the first one is set up the PLL. So the first part is you have to decide the CCLK, you have to decide the F oscillator. CCLK is processor frequency, F oscillator is the oscillator frequency. Then you have to calculate the values of M to configure the M cell bits. M is equal to CCLK divided by F oscillator, and M cell is actually M minus 1. So 1 less than the actual bit, that is given there as M cell. Then P value. So first part is you have to find out the value of M multiplier by using CCLK and F oscillator. Okay, the next one is P. For that you have to set the P cell bits. Okay, P cell bits are going to decide your P value, and P value is actually decided by FCCO. Okay, so though your CCLK and F oscillator are fixed, or those you are going to design for your system, still you have to put it those two things in a limit such that your FCCO is within the given defined frequency limits. Okay, so for P cell bit, what is the value of P that is given in this table? Just remember that when P cell is 0, it will be 1, 0, 1, it will be 2, 1, 0, that is 2, it will be 4, 1, 1, that is 3, for it is 8. So for the 4 combinations of 2 bits, it will be 1, 2, 4 and 8. These are the 4 options available with the divider. Next, here we will do some calculations for one example. Here we have taken the CCLK is equal to 60 megahertz. Okay, CCLK is equal to 60 megahertz, and we want to calculate the FCCO. Okay, so FCCO is equal to CCLK into 2P, or I can rearrange it like this. P is equal to FCCO divided by 2 into CCLK. Okay, now we know that for FCCO the limit is given as 156 megahertz to 320 megahertz. So we will put the upper limit and lower limit there, and we will find out what is the value of P we are getting. For example, the lower limit is 156 megahertz. If I substitute this value, I am getting P is equal to 156 megahertz divided by 2 into 60 megahertz. So here the answer we are getting is 1.3. Now if I put the upper limit there for the FCCO, that is 320 megahertz, it is 320 divided by 2 into 60 megahertz. So it comes out as 2.67. Okay. So now we cannot put these fractional numbers in the register there. We cannot feed it. So we have to consider something which is integer, and that should be in between 1.3 to 2.67. So in between this we are having, so this is the minimum value and this is the maximum value. For the CCLK value we are requiring 60 megahertz. Okay, so instead of that what I can do, I can put the value intermediate value as 2. Okay, so that is the integer value. So we have got P cell bits is equal to 2. So for 2, the P cell bits are 0, 1. Okay, so we will put the value of P cell bit as 0, 1 in the configuration register. Remember, 0 to 4 bits of configuration register are M cell, and 5 and 6 bits are P cell. So we will put the PCL bits as 0, 1 there. Next, MCell, calculation for the MCell. So M is equal to CCLK divided by F oscillator. Okay. So here one table is given, and along with that we will consider it for typical value of the 12 megahertz. So this is a typical crystal used for LPC2148, or this is a standard value of the crystal used for LPC2148, and we are requiring the CCLK of 60 megahertz. Therefore it comes out as CCLK is 60 megahertz. So 60 divided by 12, it comes out as 60 divided by 12, it comes out as 5. Okay. So M value is 5. So M cell will be 5 minus 1. So here you can see that for 12 megahertz, M is coming as 5 because it is 60 divided by 5. Okay. And 5 minus 1 is 4. So I am getting the M cell value is 4. Then P value I am getting is 2. Okay, and value in P cell is 1. So what is the actual configuration there? Uh, 0, 1 and 5 bits are there for 4. So it will be 0, 1, 0, 0, 1, 0. Remember, I am talking about 5 bits. So if I want to write 4 in 5 bits, it will be 0, 0, 1, 0, 0. And if I divide it in the group of 4 bits afterwards, each in group of 4 bits, this comes out as 4 and this comes out as 2. So you are getting the configuration register bits as 24. Okay, so this is we have calculated for one typical frequency of 12 megahertz. Okay, we have seen it. Similarly for 5 megahertz, multiplying factor will be 12. So values in M cell will be 11 and the final value of the PL configuration resistor is 2B. For 10 megahertz it is 25, for 12 megahertz it is 24, for 15 megahertz it is 23 and for 20 megahertz it is 22. These are typical values of the crystal given there 5, 10, 12, 15 and 20. Next, it's like a lock. When you want to change the values in the PLL, you must work with PLL feed register. And not only PLL feed register should be loaded with a typical value, but it is a sequence of the typical values. So the sequence is AA and 55. So first you are storing AA in the PLL feed register and then you are storing 55 in the PLL feed register. Okay. So two values are stored in PLL feed register AA and 55. Then your actual PLL will be updated here. Otherwise, these values will not be updated. Configure register's values will not be updated. So second step is apply feed sequence. Third is wait for PLL to lock and then connect. So I have told you that first you have to enable it and then you have to connect it. Okay. So first you have to make PLL 0 con register is equal to 0 as 0. Sorry, I think that is remaining there. I will put it here. It will be PLL con register, PLL 0 control register. It should be first put as 0, 1. Okay. So I am putting there 0 as 0, 1. And then you have to put it as, you have to wait for the status register log bit should be equal to 1. Okay, so unless it is, if it continues to 0, you will be in repeating loop. You will not come out of this cycle. And when it will become 1, you will go to the next part. So you are making it 3. Pre means you are connecting it to the other system blocks. Okay, so first we will enable it, then you will wait for the locking period, and then you will connect it. Again, you have to apply the fields request because you are writing the data in your configuration control register. So for that you are using it. Again, same sequence you have to give. First you have to give AA, and then you have to give 55. So this is the sequence. First you are writing control register is equal to 1, enable it, then configure it for the typical M cell value of 4 and P cell value of 2, and then to enable it, to make it effective, you are giving the field sequence of AA and 55, wait for the lock period, then connect the PLL, and to make it effective, you have to again give the field sequence there. Okay, and then if you put VPPDIV is equal to 0, 1, it means you are making the peripheral frequency, you are generating the peripheral frequency from this signal. So this is all about the PLL. We will see the remaining part, that is peripheral frequency, in the next the further programming there, or the further peripherals present in the LPC214. So we will stop here. Thank you.